Hey everybody, in the last video I introduced the idea of a continuous random variable, and then this notion that for a continuous random variable, so if I have x is some continuous random variable, we said the way that we find probabilities is that they will have these probability distribution functions, right? So I'm just drawing some weird shape where this horizontal axis represents data values, and when we want to figure out areas, the way we do, when we want to figure out probabilities, we figure out areas, right? So if, for instance, these were two values A and B, the probability that x was between A and B was given by the shaded area, right, in that little sketch, okay? So I also said we are not going to look at things that are very complicated in terms of figuring out areas. We'll either be using technology to do that, so we'll look at something called the normal curve with some detail in the next couple of videos. Or the shapes will be simple enough that we don't need anything very complicated to figure out the areas. And typically it's just going to be rectangles. So we're going to talk about that right now. So what we're talking about right now is what's called the uniform continuous distribution. Okay, so the uniform distribution is a distribution for a random variable, continuous random variable, where all the outcomes have an equal probability of happening. They're all equally likely, right? So in the previous video, I did an arrival time of a technician, right, where all the times they could arrive were equally likely. Or I've seen tables of smile times for infants, right? So that they're distributed evenly over some time interval. Time's a pretty typical one for the uniform continuous distribution, or weight can sometimes be that way too. So what will happen when we have a uniform distribution, okay? Well, let's say x is a continuous random variable. And what we might write is this symbol to say that x is distributed uniformly. And what we usually give is what are the smallest and highest values. So remember when we did the binomial distribution, we had to give the number of trials and the probability of success. When it was the Poisson distribution, we had to tell the average number of successes over an interval. For a uniform distribution, we need to know what's the smallest and what's the highest value that can happen for this variable. And we'll do an example in a minute to make this all a bit clearer. But when we know this, as long as we know these two numbers, we can figure everything else out, right? The picture is this. So here is there's our distribution, and there's our axes, and our distribution, because it's uniform, because all outcomes are equally likely. Remember we said these probability density functions, these curves like this one up here that we'll use to find areas, represent which things are more likely than the other by how high they are, right? And so since everything's equally likely, we get a horizontal line, the same height above each. The horizontal axis gives us the data values. Okay, and we could say the vertical axis gives us something like the relative probability is probably the best way for us to think about that now. So this is our distribution, right? We can think of this as kind of a picture of the sample space. All the possible outcomes are represented in this picture. We also know, for instance, things like the expected value, right? What's the expected value of this distribution? Well, it is exactly in the middle, right? That's our expected value, that if we kept running whatever experiment this has to do with over and over, sometimes we get values down here. Sometimes we get values up here, but on average, it would be in the middle, the average of those two. And we won't use this one as much, but it's neat to know that we also get the standard deviation, right? Remember the idea of the standard deviation. One way we can think about it is how far does the typical piece of data stray from the expectation. It's not precisely how we can think about it in this context, but it's still a reasonable approximation to it in our head. And it has this nice formula. So when we recognize we have certain patterns, we get a whole bunch of the work done for us. We don't have to think very hard, right? Going through naming all those events and things that we've done in some past videos. And then when we want to compute a probability, right? So for instance, if I wanted, let's use a color here. Let's say I wanted to know the probability that my random variable x was between two values, C and D. So let's put those in here, right? They're just any two values in here. That this probability is going to be equal to this area, the shaded area in here, right? So this is our, well, let's figure out how we can compute this shaded area. It's pretty straightforward. It's a rectangle. We need to multiply the height times the width. Right? The width is pretty straightforward, so I'm going to leave a space for the height. The width is just the difference between these two numbers, right? If this was 7 and this was 3, that'd be 7 minus 3, 4 units wide. So the width here is just D minus C. The question is, what's the height? Well, we did this example in a previous video, but it's worth doing again. One thing we know is that the probability that this variable is between A and B is 1, because this is the entire sample space, and so it's just saying what's the probability that any of the outcomes happen, and that's certain. Whatever all the possible outcomes are, one of them has to happen. But that's also should be equal to the area of this rectangle. The area of this rectangle is B minus A times the height, right? Whatever this height is, so this is the distance I'm calling the height. Well, we can solve this equation and see that the height must be equal to 1 divided by B minus A in order to ensure that the area is 1. Okay, so that's how that has to work out. So now we have that piece in here, and so we can see that our probability is given by that, right? But if this looks like a whole bunch of algebra and complication, just look at this picture. It's the area of a rectangle, right? The key thing to remember for these uniform distributions is the width is always the minimum to the maximum, and the height is always 1 over the difference between them, right? In this way, to make sure that it's a rectangle whose total area is 1. Okay? All right. So let's do a little example. Okay, so I'm going to do a let's create a little situation. Let's say that you're going to catch your train that you commute with, right? Okay, so you show up to the train station. Well, let's say it this way. There's a train. You know the train comes every 10 minutes, but you don't know the exact schedule. You don't know what time, or maybe let's just say you don't have a watch on you. You just know that it comes every 10 minutes. And so you arrive and there's no train, right? And you don't know if it just pulled out or if it's been gone for quite a while. So you don't know at all about when it's going to show up, other than it shows up every 10 minutes. Okay, so we are going to say that all the times are equally likely, because there's no way to know whether you're at the beginning or end of this interval. It's all equally likely. And so all arrival times from, we'll say 0 to 10 minutes are equally likely. Okay. So let's ask a couple of questions. First of all, I want to answer 3 questions. I want to know, let's say it this way, how long do we expect to wait, right? And I kind of mean this in a very probability sense. What's our expected value for the wait time, okay? We'll answer that question. Let's ask, what's the probability we wait more than 8 minutes? Okay, so let's start with those 2 and then move on. So one thing I want to stress is uniform distribution is our simplest continuous distribution. We're gonna look at a much more complicated one. And one of my goals right now is for us to practice using our notation correctly. So even if you feel like it's a simple enough problem to sort of think through and get the answer, it's good practice to go through the steps that I'm going to go through here. So I'm going to start by naming a random variable. I'm going to name the variable W is going to be the wait time in minutes. Okay. And according to what the problem says, W follows a uniform distribution. All arrival times are equally likely from 0 to 10 minutes. Okay, so we're going to pretend we live in one of those cities where they have a very, very punctual train system, right? That we can count on this. Okay, and let's answer the first question. How long do we expect to wait? And for that, I'm just going to look at what I wrote over here. This expected value. So our expected wait time, mu, is just going to be 10 plus 0 over 2, or 5 minutes. Right? And to be clear what we mean about that, what we really mean is when we talk about our expected value is if we were to do this every day and show up, there would be days where we'd only wait 10 seconds, and there'd be days where we'd wait almost the entire 10 minutes. There'd be days when we'd wait 7 minutes. There'd be days when we'd wait 4. And on average, our wait time would be 5 minutes. That's what we're really saying on this. That is, we did this over and over again, the average would move towards 1. Okay, before we answer the next question, I want to draw a picture of this situation. So let's go ahead and do that. I'm just going to sketch out 0 to 10 minutes. Right, 0's over here. This is in minutes. It's our wait time. Oops, that's an M, wait time in minutes. And it's just a horizontal bar from 0 to 10, right? The height, remember what we said over here, this height is 1 divided by b minus a, the end of the interval minus the beginning of the interval, 10 minus 0, or 1/10. So this is a rectangle from 0 to 10 with height 1/10. Okay. So when we ask the question, what is the probability that we wait more than 8 minutes, we're asking what's the probability that x is greater than 8. Okay. And we come to our, let's mark off 8 is probably about right here. Probabilities are given by areas. The area in question is this rectangle here. Right. So what is its area? Well, we see from 8 to 10, 10 minus 8 gives us the width of 2. We have the height of 1/10. And so we end up with 2/10, or 0.2. Okay. All right. So that's it for what's going on here. But what I want to do next is mess this up a little bit, or make this a little more difficult. So I'm going to clear some space over here. Give me just a second. Let me move my, sorry, just take a second here. All right, that's the pen. So what we're going to do is ask a slightly different question, which is, what happens if we now have been there for several minutes, right? So remember we asked what's the probability that we wait more than 8 minutes. What if I've already waited 3 minutes, right? So I ran down there, the train hasn't showed up. Maybe I'm late to get somewhere and I'm really hoping it shows up soon, and I want to know how likely it is that it's not going to show up until those last couple of minutes of possibility, right? Which might make me late. So in the beginning, I'm pretty calm, but then 3 minutes go by and I'm starting to get increasingly worried about my prospects of being on time. So now I'm asking the question, if I've waited 3 minutes, what is the probability I wait more than 8 total minutes? So not 8 more minutes, but in total, I wait for 8 minutes. Okay. So the way we do this turns out to be a conditional probability, and I'm going to do it in 2 different ways. So first, let's show that it's conditional, or at least write it down the right way. So now I'm asking a similar question that I asked over here. What's the probability I wait more than 8 minutes? Oh shoot, I'm using X when I had named this variable W. Let's fix that. I might as well. It's nice to have consistency. All right, sorry, that should have been a W. This should be a W. What's the probability I wait more than 8 minutes? But now it's given, that I've waited at least 3 minutes already, right? At 3 minutes time, my wait time has to be at least 3, okay? And you might want to put this in there. If you recall in the last video, for these kinds of areas and these kinds of problems, those little details actually don't matter. It's one of the rare times when we can be a little bit careless. And so I'm not going to make a big deal about that. I'll throw it in, and I don't like having them different for some reason. So one thing you might remember is a rule we had for conditional probabilities. The probability of A given B is equal to the probability of A and B divided by the probability of B. So let's try using that with this. So this is like my A, this is like my B. So this becomes the probability of waiting more than 8 minutes and more than 3 minutes divided by the probability of waiting more than 3 minutes. Okay, so the top one's a little bit silly, right? If waiting 8 minutes and waiting more than 3 minutes is really just waiting more than 8 minutes, right? If I've waited 8 minutes, I've already done this. And so the probability of doing both of these things is the same as the probability of waiting 8 minutes, which we already figured out. I'm going to keep this as fractions because we're going to have to do some division. I don't want to deal with ugly denominators or ugly decimals. So we already figured out the probability of waiting more than 8 minutes, which again is the same as the probability of waiting more than 8 minutes and more than 3 minutes, because if you wait more than 8, you've done the part where you wait more than 3. So we got to divide by the probability of waiting more than 3 minutes. Well, we can look at our picture again. So if I imagine a rectangle now, use a different color. Let's use green maybe, right? Waiting more than 3 minutes is this rectangle, this area. And I know that the width of that rectangle is 7, and the height is 1/10, right? So 7 from 3 to 10 gives me the 7, and the height was 1/10, so 7 times 1/10 is 7/10, right? And to divide fractions like this, you multiply by the reciprocal of the denominator, and so I end up with 2/7. Okay, so that's one way to do this problem. 100% correct, no problem with doing it that way. I don't favor one way or the other. Let's answer this question a slightly different way. I could also think I could make a new random variable. X is a wait time. X is the wait time from, let's say, 3 minutes after W began. This is kind of a convoluted way to write this, but all I'm saying is the wait time starting from after those 3 minutes have passed, right? Every time after those 3 minutes is still equally likely. So the first 3 minutes didn't happen, but the rest are still equally likely. So this still follows a uniform distribution, except this one goes from 0 to 7, right? Because we know that the train is showing up in 10 minutes, every 10 minutes, but we already waited 3, so there can't be more than 7 minutes left. It could roll in right now, or we could have to wait up to 7 minutes, okay? And we can draw the probability distribution for this. It goes out to 7. It again looks like a rectangle. Its height is going to be 1/7 to make the whole area 1. And so now, right, the probability that we wait more than a total in 8 minutes, well, we've already waited 3, so it's like saying the probability that X is greater than 5, right? We've already waited 3, so waiting more than 8 total means that we wait at least 5 more. So our picture, if this is 5, we're looking for the area of this rectangle, right, which is easy enough to figure out. The width is 2, the height is 1/7, and we get the probability of 2/7, which, as expected, matches with what we got up there. Both of these ways of doing this are reasonable, and so they should come up with the same response. Okay, so that's all I'm going to say about uniform distributions in this video. A lot of the examples are pretty similar, right? It's a pretty straightforward idea once you wrap your head around it. Okay, that is going to be it for this one. Thanks, everybody. I will see you next time.